Welcome to this explainer. All right, let's just dive right in. Today, we're going on an epic journey. We're looking at how our planet literally recycles its own surface over and over again. We're cracking open the secret diary of planet Earth. And guess what? That diary is written entirely in sedimentary rocks. It's kind of crazy to think about, right? How does a massive, towering mountain turn into fine dust and then somehow back into solid stone? It's the ultimate recycling program, turning seemingly boring rocks into nature's history books. But to read those books, we actually have to start with the destruction of what's already there.
Which brings us to Phase 1, breakdown, weathering, and erosion.
You see, the relentless physical and chemical beating that rocks take from the elements leaves behind a very specific, loose concoction. It's a mix of tough minerals and stable clays that we call regolith. Basically, this regolith is the raw material, the fundamental building blocks for all of our future sedimentary rocks.
And during this weathering process, it's literally a geological survival of the fittest. The tough minerals, like quartz, they survive the beating beautifully. But the weaker ones, like olivine, they get chemically altered and completely obliterated by the elements.
So once the rock is completely broken down, we enter Phase 2, the Great Migration. Now that we've got this loose regolith, agents of erosion like wind, water, and ice just swoop in and carry it miles away. And as these particles travel, the energy needed to move them actually acts like a giant, natural sorting machine. Wind is like a total perfectionist. Super efficient, organizing grains perfectly by size. Water is, moderately efficient. But glaciers and landslides, they are nature's hoarders. Totally inefficient, just dumping massive boulders and microscopic dust together in one giant chaotic pile. And hey, this sorting efficiency actually matters a ton. A poorly sorted mix has terrible porosity because all those tiny dust fragments completely clog up the gaps between the larger rocks. But a well-sorted sediment, it keeps all those open spaces perfectly clear. But eventually, the wind dies down, the river stops flowing, the sediment settles, and we enter Phase 3, becoming solid rock. Think of this as the resurrection phase. This transformation happens through diagenesis and lithification, specifically at temperatures under 300 degrees Celsius. It's basically a three-step recipe. First, the insane weight of the overlying sediment compacts and squashes everything together. Second, heat and pressure cause the recrystallization of certain minerals. And third, cementation kicks in. New minerals form in the watery gaps and act like superglue. Literally, loose dust is squashed and glued back into solid stone. So we've got solid rock again. How do we classify it? Welcome to Phase 4, two families of rock. We actually categorize these new sedimentary rocks into two major groups, based entirely on how their ingredients got to their final resting place. The whole secret here is the difference between autochthonous rocks, which formed exactly where we find them today, no travel required, and allochthonous rocks, which are built from pre-existing rains that went on a seriously long journey before piling up.
That stay-at-home autochthonous family, it includes chemical precipitates like halite and gypsum left behind when ancient seas evaporated. It also includes organic deposits, think coal, which comes from plants that suffocated in ancient oxygen-depleted swamps where decay was stopped dead in its tracks. And finally, residual deposits, like bauxite, which form from extreme chemical leaching of the ground.
But here's the crazy part. Over 90% of all sediments actually fall into the allochthonous terrigenous category. They're the travelers, and since they are transported grains, size is the single most important thing for classifying them. We split them into three main buckets: the tiny argillaceous mud rocks, the medium arenaceous sandstones, and the massive rhodaceous rocks, which are basically big gravels and cobbles.
Now, when geologists look at the absolute finest of these sediments, the mud rocks, they hunt for specific properties. Take the word shale, for example. We only use that term for a mud rock that is fissile. What does that mean? Well, it means the rock easily breaks apart into incredibly thin, almost paper-like sheets. It's a dead giveaway that it settled out in super calm, quiet waters. Jumping to the total opposite end of the size spectrum, we've got diamictite. This rock is pure chaos. It's a poorly sorted, coarse-grained rock with huge chunks just floating around in a fine mix of sand, silt, and clay. It is the exact fingerprint of a violent event, like a massive landslide or a glacier just dumping a messy mix of everything it scooped up along the way. And the actual shapes of these fragments? They're like clues in a geological detective story. Smooth, rounded clasts in a conglomerate tell us that the rocks tumbled and rolled in a high-energy river or along the coastline for absolute ages. But sharp angular clasts in a breccia, that means they just shattered and fell down a slope. Barely any transport at all.
Which brings us to the final, forensic stage of our explainer. Phase 5, reading sedimentary structures.
When we look at massive horizontal bedding planes, it's wild to think about what they represent. Every distinct layer or bed is a period of continuous deposition. But those flat planes separating the beds, those actually represent vast, completely silent periods of geological time where absolutely nothing happened. Just a pause in the Earth's diary. We also find some amazing clues hidden inside the beds themselves, like graded bedding. When sediment settles in water, the heavy, coarse grains sink to the bottom first, and the lighter ones settle delicately on top. Finding this pattern today is like finding a geological compass. It unequivocally points to which way was originally up when the rock formed, even if the Earth's crust has completely flipped the rock upside down since then.
Then there's cross-bedding, where the internal layers are actually inclined at an angle. This happens when an advancing front of sand, picture an ancient desert dune or a flowing river channel, gets frozen in time. It literally preserves the exact direction that ancient winds or waters were moving. How cool is that? Sometimes the ancient environment leaves behind literal imprints. Finding fossilized sun cracks or the tiny little craters of rain pits hidden inside these rocks, that is absolute unequivocal proof that the sediment was exposed to the open air before it was buried and turned to stone. So the next time you casually pick up a rock, ask yourself, what ancient environment, what epic, violent journey is hiding inside it? Remember, rocks aren't just static, boring stones. They are dynamic diaries of destruction, migration, and resurrection, just waiting to be read. Thanks for joining me on this explainer, and I really hope this sparks your curiosity to keep exploring the incredible history right beneath our feet.